Hi, welcome to VSEPR Theory Shapes. That's Valence Shell Electron Pair Repulsion, VSEPR. Look at the back of your reference sheet. Yeah, you have these different shapes, but this is going to be part of how you determine polarity of not just bonds we talked about already, but this is molecules, which has a dramatic effect on their properties. So you've got linear. Simplest, most direct. If you only have two elements, it has to be linear. These are a couple different representations. You have some structural formulas. You have some ball and stick type models. So the idea here is that the unshared electrons generally are not drawn on these structural formulas, but the number of bonds are. So here's some examples for linear. These can be polar or nonpolar. Bent. Bent is illustrated, as you can see the structural formula, that it is not a straight angle. They are not showing the ideas of only what is bonded. They are showing the actual, not realistic angles, but that there are angles. So something like water or oxygen difluoride or hydrogen cyanide or carbon dioxide. Don't worry about the angles. You're not going to have to memorize how many angles or what. I even believe that's on the reference sheet, but we're not looking at that. The idea is that the central atom is at an angle, not 180 degrees straight across. Trigonal planar, all of them are in the same flat plane. However, the unshared pair of electrons in the central atom is replaced with a third bonded atom. So you have three things bonded. They can be double bonded or triple bonded or single bonded. Well, I guess not triple, because then it couldn't be bonded to three things. Now, we can see something like trigonal planar SO3 is symmetrical, that if you divided it, oof, that was terrible. If you divided it along a central line, as I'll try to do here, it's the same on the left and the right, same on this axis, same on this axis. However, over here with the SOCl2, it may be symmetrical that way, but not symmetrical that way, from left to right on that. And there's an oxygen on one side and a chlorine on another. That plays a role in polarity. Trigonal pyramidal. So this would not be a good representation of a structural formula, neither would this. This is showing you the way it's bonded. This is the 3D structure that you may be expected to draw. The idea is that the nitrogen and fluorine, shown with the line, I'll see here, show with the line here, this is in the same plane as any two would be. However, this fluorine, right here, this fluorine here is coming towards you in a three-dimensional way. This fluorine over here is pointed behind the nitrogen, so going backwards. So think of a tripod to where these two are in the same plane. This one's coming towards you. This one's going behind the nitrogen. Same goes true over here. We have these in the same plane. This one coming towards you, illustrated by this triangle here. And then these horizontal lines illustrate that it's going behind the phosphorus. We generally also would not be drawing the unshared electrons up top. Structural formulas generally don't show unpaired electrons. Again, if you look online, you'll find a variety of different models, but these two here are the best representations in a three-dimensional shape. When we look at what's called tetrahedral, similar to trigonal pyramidal, but it has four bonded instead of three in an unshared pair. Again, 3D structure, you can see that these are in the same, use my pointer, these are in the same plane, much like a bent would be. This one's coming towards you, this one's going behind. This would be a ball and stick model of the same molecule. Here again is a poor representation, I'll cross it off, of a 3D structure. It's more like a Lewis structure, but again, not so good using the idea of mixing these because it confuses people. The idea of Lewis structures show bonding. 3D structures show shape. They should not be mixed between. So the idea, these are all in the same plane. This one's coming towards you, this one's going behind the carbon. Next we have trigonal bipyramidal, like trigonal planar, but has 5 bonded atoms to the central, 2 perpendicular to the plane. So again, this trigonal pyramid really should have, this is more like the Lewis structure, while the 3D structure is like this here. So these are all in the same plane, 90-degree angles, all flat. This has a chlorine going backwards, chlorine coming towards you. This again is the same representation, but more in a Lewis structure. Again, mixing both a 3D structure and that. This is really a poor representation, but that's why I wanted to show you. A 3D structure would look like this. A Lewis structure would look like this, although I would demand that you use electrons, not lines. I don't want you to confuse the two of a 3D structure and a Lewis structure. Our last is octahedral, similar to none, has 6 atoms bonded to where you have all angles being 90 degrees from each other. So again, we've got our semi-Lewis structure over here. However, over here we get a nice representation of a 3D that these are all in the same plane, almost like a linear, and that we have 2 going back and 2 coming towards you. Also shown in this idea of what this would be, selenium hexachloride 2- ion, with 2 coming towards you, 2 going back, all of these in the same line. So the shape is 1/2 of the concept of something being polar or nonpolar. So I've already highlighted if something would be polar based upon shape alone and what conditions that would be under. This would be important for you to know. No, you do not get to use this for any kind of test, but what I want you to do is fill in these boxes here with examples. Describe examples of if there's lone electrons around the central atom, Lewis structure, that means the dots, 3D shape, like the structures you've seen so far, to get some practice with all of these. Either find ones online in your book, but try to get some different experiences than what you have already found in your notes. Come in with your questions.